So here's a third definition of acids and bases. We talked about Arrhenius and Bronsted-Lowry, and this is the Lewis definition. And this Lewis is the same Lewis who did the Lewis dot structures. He's an American scientist. This model focuses on the transfer of an electron pair. Instead of thinking of the transfer of a proton, it's the transfer of an electron pair. So then an acid is an electron pair acceptor, and a base is an electron pair donor. Bronsted-Lowry focuses on the proton. Lewis model focuses on the electron pairs. So when the hydrogen ion attaches to an ammonia molecule, we can look at this as a transfer of an electron pair from the ammonia to the hydrogen ion. And so that makes NH3 a base. It results in the same identification of acids and bases. It's just what side of it are you looking at? The Lewis definition is important in organic chemistry. Okay? And many of you guys are going on to that next year. So that's why we're talking about it. So this expands the definition. The definition expands which substances can be considered an acid. Because now you don't have to have a hydrogen ion. The other two definitions, you've got to have a hydrogen ion. In order to donate a hydrogen ion, you have to have one. So here we can have acids that don't have hydrogen. So an example is boron trifluoride. So this can act as a Lewis acid with ammonia, the base. And so it accepts this electron pair and forms what's called an adduct. So these two are coming together, they're forming one molecule. This works because the boron trifluoride has an empty orbital. That empty orbital can accept that electron pair. So Lewis acids will either have an empty orbital or the ability to rearrange electrons to create an empty orbital that can accept an electron pair. Here's a couple of examples. So here's aluminum trichloride. So when we look at this Lewis dot structure for aluminum, what do we notice about the aluminum? It doesn't have a complete octet. That means there's an empty orbital there. So that empty orbital is going to get along really well with this lone pair of electrons. And so these can come together. The aluminum chloride, trichloride, has essentially accepted that pair of electrons. The ammonia has donated it. So this is acting as an acid, that's acting as a base. Here's another example where we've got boron trichloride, again, with an empty orbital. It doesn't have a complete octet. And here we have an ether where we have this oxygen in the middle, and the oxygen has lone pairs. This can act as a base, donating an electron pair to the boron, which acts as an acid by accepting the electron pair. And it forms this adduct. Just looks like a big old mess.
Makes the boron act as an acid?
The boron is acting as the acid. The compound, really, the boron trichloride, is the acid because it's accepting the lone pair.
From the oxygen?
From the oxygen. And the oxygen in this compound is acting as the base. So we end up identifying the same way. We'd identify ammonia as the base, but there's no hydrogen ion being transferred here. And so the other definitions don't cover this. But these are acting as acids.
So it's a little flip-flop from the Bronsted definition, as in this case that acids are the ones receiving?
Yes.
As opposed to giving.
Right. So it's, I had an analogy and it just disappeared. Went into the ether. It's like gaining a positive or losing a negative. It's the same difference, right? It's just, what are you focusing on? So are we gaining a hydrogen ion or losing an electron pair? It's the same thing for most acids and bases. But here we don't have any hydrogen ions to mess around with, and so we have to look at the electron transfer. Some molecules can rearrange their electrons. So here we've got water, which we know is a Lewis base. Well, water can be an acid or a base, but it's got these lone pairs that it can donate. And that's what bases are going to have. Here's carbon dioxide. Carbon dioxide doesn't look like it would be able to accept accept a lone pair, does it? But it can rearrange its electrons. The electrons in one of these double bonds can become a lone pair on the oxygen. And then the carbon can accept this lone pair from oxygen. And this hydrogen, yeah, it's complicated. This is a preview of organic chemistry. There's a lot of curved arrows showing where electrons are going. So we've got these electrons going up here. So there they are right there. And these electrons are forming a bond with the carbon. So there they've made that bond. Now there's this hydrogen on this central oxygen here. Those electrons are going to go back to the oxygen. These electrons on this oxygen are go on to this hydrogen. And so the hydrogen ends up over here. It's kind of this weird little circle-y thing, yeah.
Why does the hydrogen have to move from one oxygen to the other?
That's a good question. Why can't the hydrogen just stay here? Oxygen tends to form two bonds, and it is most stable when it has two bonds and two lone pairs. If we leave it like this oxygen has three bonds, and this one only has one bond. And so if you look at formal charges, the formal charges are really high here, and if it rearranges like this, then the formal charges are lower. Now that doesn't explain why it does that, but I don't think we really want to talk about why. Not right now. So carbon dioxide can act as a Lewis acid. This is why we boiled the water to make our sodium hydroxide, because carbon dioxide does dissolve in water. And so just regular water that's been sitting out open to the air has carbon dioxide in it. Carbon dioxide can act as an acid. If it can act as an acid, then it's going to mess up the concentration of your sodium hydroxide, especially if it's continually open to the air and you can just have more carbon dioxide coming in, and it'll form carbonic acid. Any questions? Some cations can also act as Lewis acids. And we mentioned that small, highly charged cations can be acids, but we didn't explain why. So here's aluminum 3+ ion. So this is a small, highly charged metal ion. And it has empty orbitals because it's lost some of its electrons, right? So here we have water acting as our Lewis base. You have 6 water molecules attached to this aluminum ion. So the aluminum is accepting lone pairs from the oxygen on the water. The aluminum's acting as the acid, accepting the lone pairs. The water is acting as the base, donating the lone pairs. Y'all seem just a little stunned. Like, what? So the good news is this isn't a big deal, okay? But I've told you about it now, so there it is.